Hello everyone, my name is Areg Melik-Adamyan. I'm from Intel, and I'm presenting you today a framework that we developed over DPDK to help DPDK be more cloud native. We look to the problem of performant network functions from the top, from the ordinary programmer's perspective, not Ninja's perspective, and from their perspective, the developing performant scalable network function is kind of black art. There's a significant amount of time spent in scaling, parallelism, building infrastructure, multi-core scaling, deployment, chaining, etc. And there's a need to help to gap these problems for the usual programmers, and we built this framework, and there's a good quote from our customer that you have a problem which is usually custom, and you can easily describe it on a whiteboard or napkin, but you can get off-the-shelf solution for it, especially if you want to deploy it to the cloud. And you want to solve it just by sitting down and writing your ordinary program to solve the problem. And to help that, we created this framework, and it's a kind of targeting cloud-native packet processing framework. It's built on top of DPDK. It aims to accelerate time to market for new greenfield virtualized network functions and meet demanding throughput requirements. So three main characteristics is that it's high-level packet flow graph abstraction written in the Go language. So the level of abstraction is much higher than in DPDK. Due to usage of DPDK, it provides very fast packet input-output and optimizations under the hood. And we have built-in auto-scheduler, which automatically scales network function to sustain the changing throughput requirements. This allows programmers to focus on developing the packet processing functionality, not everything around it, and brings 10x improvement in performance in terms of lines of code. So this is the high-level picture. It's an inherently open-source project. It resides on the GitHub. Provides higher-level application abstractions than DPDK. It's written in a Go language, which is language of choice for cloud-native infrastructures, software-defined infrastructure, Kubernetes, Docker, everything written in Go. And it changes the view how you program network functions from the virtualized machine. You just, instead of virtualized machine, you program it as an ordinary application which can run everywhere. And another important part is because it provides high-level abstractions, input-output can be anything. So we don't mandate source to be DPDK. It can be DPDK packets, it can be DPDK raw packets, it can be kernel structured packets, kernel raw packets, files, memory, even RPCs. Actually, it doesn't matter. We have this abstraction, and this abstraction can consume packets from everywhere. The benefits that the framework brings to developers is because Go is natively compiled language, we can directly or through DPDK leverage all Intel hardware capabilities. Due to high-level abstractions, we reduce the number of codes needed to develop function by roughly 10x. We provide run to completion of network functions in the same address space. So we mandate that it's better to be done in the same address space, and we do this run to completion. We have built-in scheduler which does scaling, so scaling is done automatically at zero cost for developer. And due to carefully designed architecture, we provide similar performance with C per box. So this is well-known simple forwarder from DPDK. It's about 2,000 lines of code. This is the same forwarder written in NFF-Go, and it's about 54 lines of code. Line rate, we achieve line rate at 256 bytes, pretty similar to DPDK, and in that matter we are on par. So here there's a slight problem with 64-byte packets, which is due to hardware problems, not software. So on software side, we are on par with DPDK. So what comprises these framework? There are very few architectural concepts and design concepts that we used. They are pretty much orthogonal to each other, which allows to create very effective flow graph, abstraction graph. So there's a notion of flow, which is an abstract flow. It's not the same as TCP flows as everybody else, maybe not a very good name, but completely represents what it does. So it's an abstraction that connects a flow function, and you can send, receive, you can split, I'll show later, merge, swap, and there's an abstraction packet, which is a high-level abstraction of packet, which is practically the pointer to the MBUF from DPDK. And you can get all the needed information, MAC, IPs, data, etc., from the MBUF with the offsets. And this is automatically extracted by the framework before any user-defined function kicks in. There's an abstraction called port, which is practically the door from where you can get packets. And you can send, receive data packets from the port and to port. And port can attach to anything. It can attach to DPDK physical port. It can attach to KNI port. It can attach to kernel, file, buffer, RPC, whatever you want. There is a set of abstractions called rules, which provides you effective ways to deal with the packets in your user-defined packet processing functions. This is the processing standard functions, which allows you to create your packet processing graph. So there's a send receive, which attached to ports and actually acts as an input to your flow graph and output. There's a stop, which terminates the flow. There's a generate function, which creates the packet, and you can send it to any flow you want. Read-write are mainly for debug perspective. It allows you to read-write from the PCAP files. Merge is an abstraction which allows you to merge several incoming flows to the one outgoing flow. And its counterpart is split, where you define your split function, and it splits incoming one flow to several outgoing flows. I'll show it later in the example. There's a function called separate. It's mainly created for the metering purposes. It allows you to get a flow of packet from incoming flow without terminating the original flow. And partition is also for debug perspective. You can periodically examine several packets from your incoming flow. So packet modification functions is mainly a set of handle we call them handle functions, which allows you to do either inflow modification of packets, or you can extract your packets to different flow and do handling packets there. And there are a set of predefined functions for dealing, helper functions for parsing and dealing. So we support parsing for L2, L3, and L4 levels. You can initialize packet fields. We have built-in encapsulation, decapsulation supporting GRE, MPLS. And here is a small example. I hope you see it, where we create this processing graph to do simple ACL forwarding. So this is the structure that will hold the rules. It's defined in the framework. Then we do the flow system in it, 16 cores. We tell the framework that we can use up to 16 cores. It will not use this 16 cores immediately, but we allow him to scale up to 16 cores. Then L3 rules get rules from the 5-tuple, so it just parses the 5-tuple ACL file and stores them in the L3 rules. Then here we say that input flow is the physically attached to the port number 0 in DPDK. And output flows is an array of outgoing flows which will be defined by the function which we called splitter, and is defined lower, which actually what it does, it gets the packet information, applies the rules from the 5-tuple, and returns a number which we use to send it to port number 1, 2, or 3. Then in a cycle, we just send packet to the specified port. And then we do system start, and it launches DPDK, get the flows of packet, and start processing. This is how it's done. This is example. The graph is arbitrary. You can create any graph you want. There's no mandating steps, nothing, whatever you want. This allows you to do your custom packet processing very easily. The only requirement is that you need to have starting point with the receiver, but you don't need to have outgoing, the exit node as the send. You can stop or do whatever you want. So from the programmer's perspective, this is an ordinary program. Nothing else. This is some examples of the performance that we get and of the functions that were developed and used. So the first one, it was simple net, and the question was how much closer to the line rate on the 40 gig Intel card we can get. And here are some data that you can see here. So on 8 cores, we are getting line rate on 50K connections. So this is higher than usual DPDK, for sure, but this is because we are using higher level abstractions and framework where we differently allocate cores. We allocate 1 core always for the scheduler, which runs on this dedicated core. And based on the number of, on the throughput, we can allocate 1, 2, 3, or 4 cores more for the input-output. So we will always use fixed number of cores more than DPDK, but this is fixed number of cores. So the customer's code which was written on DPDK, we're using 5 cores for comparison. Another examples, there's a production grade edge NOT, which is used for in the production system of one of our customers. It is a little bit different. It supports IPv6, and the control plane for this function is written in using gRPC. That was one of the requirements. Everything is open source. You can go try it. It's fully fledged net for cloud, for edge cloud. Another thing which we did with another of our customers is we tried to prototype fixed P gateway BNG for the upcoming 5G networks. It was mainly for households, and this code is also on the performance on par with the DPDK implementation. This code uses 5 more cores because there is a KNI involved, and we do here a thing called shadowing for the control plane. So all the ICMP packets it was a requirement of the customer to go to the kernel and trigger the route table there. So for that, we use a little bit more cores. But on performance part, we are on par with the C implementation. So how this helps in going to being more cloud native. So our framework created with the abstraction level on the level which allows you to actually forget about all the dependencies underneath and just focus on the functionality. And you can package your function using NFF-Go in any convenient way. It can be virtual machine, it can be container, or it can be just bare metal applications. So inherently, the most important part that packet processing application logic is fully decoupled from deployment. And this eases the deployment part. We came up with the notion of a component which we call cloud boundary node. And this is the place where we need to be line rate, and this acts like a converter of an incoming traffic to the something which will be later consumed in the cloud. And here, you can see, so this is written in NFF-Go using DPDK. It can consume Ethernet, it can consume anything. What it does, it repackage the traffic for the outgoing functions, and the functions can be virtual machines, containers, or microservices, which can run on top of any cloud runtime, including Kubernetes, and they can interact with each other in a way which is more convenient or more natural for the system. It can be Ethernet, it can be HTTP requests, IP, TCP, doesn't matter. So this is kind of comprising the microservice mode. And the only point is that we consume Ethernet traffic on the boundary node, and we produce Ethernet packet on the boundary node for the exit. The traffic inside two boundary nodes is being processed. It can be processed during, via the calls. So we just call the function which runs on the different microservice, and we do not need all this switching, which you can see the usual stuff, which you can see on the left part. So there is no rules involved. There is no package going to the VNF back and forth. Everything is directly encoded in the calling graph. So the benefits that Cloud Boundary Node brings for us is that it acts as a load balancer, classifier, and pertinent slicer, and acts as an entry and exit point for the network functions. So it clearly separates the performance because CBN is the only component we need to run on a line rate, because everything else beneath inside of two boundary nodes, we can do horizontal scaling. It separates the network topology before and after. And for example, for telcos, it's important that telcos network is not mixed with the cloud network. It separates the interfaces because you can use inside in the cloud, you can use any type of API you want. Also, it's very important that it separates the security domains, because CBN is owned, trusted, and can be developed in-house by the service provider, and it's not the third-party software. So this is the structure of a cloud boundary node. So there's an ingress, egress coming from and to the boundary node. There are 3 databases involved. One is the classifier, which helps you to classify the packet for slicing, for example, per tenant, or for policing, whatever you want to do later. The second one is the service chain configuration, which will allow you to add in the context for the next call, what is the next function that this packet needs to be sent. And there is a custom context which defines what additional metadata you need for efficient processing of this packet somewhere else. So practically it does classifying, it does decapsulation, and then forwarding to the specific network function, which does the job. Then you come back, encapsulate, and send it to the network. Yeah, so that's mainly it. Our project is on GitHub. I encourage you to go use it, give feedback, contribute it. We already have external contributors. Part of the configuration and device binding part was done by external contributors, one of our customers. And so far we are getting pretty positive feedbacks for the ease of programming, and we want to enhance and we want to go further, and that's why we need more contributors to build the community. Now I'm open for the questions.
I have a question about the coverage of the DPDK API. I mean, almost all functions available in DPDK is also available in NFF-Go, right?
You mean libraries?
Yes.
So there is a cost. Yes, the answer is yes, but it's complicated. We did very clear separation of memories for DPDK and Go, so we will not cross the boundary not to pay the penalty for the calling CGO. But if there is a need and we do not have that function, we always can fall back to the call of DPDK directly. But it will come with some penalty because you are crossing Go memory to the C memory, and this is done through the component of the Go called CGO, and you will spend from 50 to 300 cycles just for call.
Okay. And related question is that is NFF-Go program can be aware of the existence of the offload, like SmartNIC?
Sorry, can you please repeat?
Can NFF-Go program can be aware of the existence of SmartNIC?
Can NFF-Go program be embedded into the SmartNIC? That's the question.
Can be aware of the...
Can we use SmartNICs from NFF-Go?
Yeah.
Yes. So if there is an API which allows you to get something from the SmartNIC, then yes.
Okay, thank you.
Hey, so just a bit more about integrating with Go. So things like layers and protocol library, do we still use those?
Which one?
Like layers?
We can use that, but it will be again costly.
But so you have replacement for layers, basically, is what you're saying. And what about in the actual functions themselves? Can we start using channels?
Yes.
But you say we take a penalty if we start using the Go scheduler.
No, you can. So from the program's perspective, NFF-Go program is just Go application. You can use all the capabilities of Go.
So why would we do service function chaining at all if we already have that capability in Go?
If, for example, you have two functions which developed separately, and they are like plugins, you need somehow to give a context how to create channel between them, and this is where the external part kicks in.
All right.
I have a question related with the service function. From my understanding, I suppose that in a cognitive environment, microservice will talk with another microservices. And in this case, we need some kind of TCP IP stack. So in your picture, we show that it looks like still the traffic based, right? From the one container, one microservice to another service. So it looks like there's some layer of the TCP IP stack. So how we handle that?
So for the IP stack, you can always fall back to the Go packet. For example, this is the Google's implementation of IP stack functions in the Go. We are planning to add some library which will provide user-level TCP stack, like MTCP or something else. But for that, that's up to the programmer to use the appropriate stack in the microservice.
Okay. Okay, understand. Thank you.
I have a question.
Yeah, go ahead.
How do you manage your Go routing? Do you share the Go routing with your C thread on the same core?
How do you, sorry, what?
Manage your Go routing.
Oh,
Do
yeah.
you let the runtime manage it, or you have to
Yes, so we do not in the framework, our scheduler, actually what it does, it pins each Go routine to the thread, and then it pins each thread to the core, so there will be no any jumps.
You ping the Go routine to thread, to the C thread, or to
To
Go
the host thread.
To Go
Yeah,
thread.
to the
Then you can ping the Go thread to a core.
You pin, the first step is to pin the Go thread, Go routine to the thread, and then you do pinning, the thread pinning to the core.
Okay. And do you share the Go routine with the C thread on the same core?
Sorry, can you?
Do you let the Go routine and the C thread run on the same core?
It's up to Go runtime.
But in your case, do you let them share, or do you let the
We
runtime
don't.
manage it?
So usually we do not run the same code.
Thank you.
Any other questions? Okay, if no, then thank you.